So far, we just investigated the network flow problem that each node represents a destination or source, but in some cases we can have a different interpretation of the nodes. For example, nodes can represent the time, so the starting point can be time 0, and then we add second year, so represent each year by a node. And you can see an example of this kind of network in the one of the example of the textbook. So as we move from one year to another year, there is a cost associated with connecting one year to another, and from second year to the third year, and from second or to the fourth year, and so on. So there is a cost with moving from one year to another. So it means that this network flow problem is very effective way to solve different type of the problem. Then let's have also in the last chapter we talked about the transportation problem, that we had supply nodes and demanding nodes, and then we had some materials that should be each node can send to destinations, and sending materials to the destination had a cost. We already solved this problem in the last chapter. Now let's look at another type of the problem, which is called generalized network flow problem. In this type of the problem, we have a set of the nodes similar to our previously talked problems, but there is some change, that there is an assumption that whenever in the previous problems we assumed that whenever we send out, it's going to receive by the node that we send it to, but there are some situations that it's not the case. For example, assume that we have an oil pipeline and there is a leakage of the oil. So if we send 1 gallon, we may end up getting half a gallon at the destination. So we call this leakage pipeline. And you can see other examples like the evaporation of the materials and so on. So in this case we want to talk about this kind of the problem, that some loss or gain may occur when we send out the material from one destination to another destination. Let's look at the examples. So in this example we have dealing with a paper recycle company. They recycle several materials using 2 different processes. For example, if they process newspaper using the first recycling process, each ton costs $13, but it yields 90%. For example, if they process 100 tons, they are going to get 90 pounds of the recycled material of the newspaper. Similarly, they have another process that if they process newspaper, they are going to get 85% of the material that they have processed, and each of these process and has a different cost. And then they have another set of the operations that convert the recycled material to the finished material. So for example, if they process the output of the recycling process of one to the newspaper one, they get each ton costs $5, and the final outcome is the 95% of the materials that they have processed. Now each nodes, they have the materials at the warehouse, for example, they have 70 tons of the newspaper, 50 tons of the mixed paper, and others. And also they have a demand, like they have a contract to provide 60 tons of the newspaper and 40 tons of the packing paper, and 50 pounds of the 50 tons of the print stock. So in this problem we want to minimize the cost associated with meeting these demands, given that we have this type of the materials and we want to convert to the we have two process to recycle them, and so we have to minimize this problem. Let's look at the problem one more carefully. So the cost, each decision variables, as we talked, the decision variables are the arcs that we have in the system. We can number each node by label each node by one number. So for example, we can put newspaper as 1, mixed paper as a 2, and so on. So as you can see, we have 9 nodes, and we have arcs that they are connecting. So the cost of this production is going to be the amount of the material that we process. So the X1, X5 is the newspaper that has been processed using the first cycling process. So the cost of this one is going to be 13 times X1 5, and then we have 12 times X1 6, that is the newspaper that they have gone through the second process, and so on. So this is the cost of the recycling, and then we have the cost of the furnishing the material. So X5 7, X5 8, and X5 9. So the cost is associated with X5 7 is $5, and X5 8 is cost $6. So we add all of these costs together as an objective function. So this is going to be our objective function, and obviously the type of the cost, the type of the objective function is minimizing. Now let's look at the constraint. The constraints that we have node 1 that we have 70 tons of the newspaper, and we know that we have newspaper can be sent out into 2 recycling materials. So there is no need to use all the newspaper, so we may keep some of the newspaper in warehouse. So inflow of this network, this node is 0, so inflow is 0 minus the outflow is X1 5 minus X1 6 should be greater or equal of minus 70. So this is the constraint for node 1. Then similarly for the node 2, we have 0 minus X2 5 minus X2 6 greater or equal to minus 50. So for all of these nodes, node 1, 2, 3, 4, we have similar process. But the situation for node 5 and node 6 and 7, 8, and 9 is different because we have leakage in the process. But still we can use the inflow and outflow process that we had. Remember that whenever we use a newspaper using the first cycles recycling process, we get 90% of the material. So we can use this in the inflow and outflow. And remember that the difference between inflow and outflow can be positive. That means we may keep some of the stock in the node 5 or node 6, so that's not necessary to use all of them. Now, so in this case, 90% of the x15 plus 80% of the x25, that means because whenever we send x15 from we just got 90% of them, so that means 90% x15 plus 80% of the x25 and 95% of x35 and 75 of x45 are the inflow of node 5, and outflow is going to be the material that we send out to news to the other stage, node 7, 8 and 9. So it's gonna, the outflow is x5 7, x5 8 and x5 9, and so the subtraction of the inflow minus outflow should be greater or equal to 0. Similarly, for the node 6 we have the same situation, so 85% of the x1 x6, 85% of x2 x6 plus 90% of x3 x6 and 40% 85% of x4 x6 should be greater than the summation of x1 x6 x7 x6 8 x8 and x6 9, so greater than equal to 0. So we have already resolved this constraint, and then the last set of the constraint that we have for the new destination. So still we are getting some percentage of this material that we already sent out. We say 95% of x57 plus 90% of the x67 should be greater or equal to 60. So that means that we are satisfying the demand of the 60, and then we can do same thing for the node 8 and 9. So basically our objective function, our constraints is divided into 3 categories. One is the raw materials that we have for the node 1, 2, 3 and 4. Because we don't have any inflow for this materials, we have just outflow. And then we have the recycling process that they are in the middle. The first part of it, which is the inflow, and they have a percentage, we can write in this way, and then we have the outflow that goes to the second stage. Also we have a similar situation for node 6. But for the node 7 and node 8, we have just only inflow. We don't have any outflow that they get material from different destinations. So this is basically our modeling of this problem. So let's solve this model. Similar way that we modeled this problem, this type of the problem in other cases, we can use a similar process, but here we have percentage of the linkage that we have, the percentage of the leakage that we may have in the case. So we set up from to 4, and the leakage between the from to 4 that we have seen, and the cost associated with each of the movement. And this column A represent the cost, represent the decision variables that we have. So the objective function is going to be the sum product of the decision variables and the cost associated with the shipping of the material, or in better word, the processing of the material. And then the inflow of the materials is so the inflow of the materials is that materials that they come into the each destination. So we use a function we call SUMIF. So here we are adding up all the decision variables. We can log them, and then Uh, remember that inflow that we had, uh, they are they have a leakage, so we have to compute the we have to multiply by the leakage percentage, so the actual material that we are getting is exact is not same as the xij that we have, so we multiply by the leakage percent, and then for all of the uh, nodes we computed. So then the function for the inflow is going to be, we use sum if, so we add up these numbers. These are the values that they are actual inflow, and then we are looking for the inflow that they comes to this specific node, and we compare it to these values. So because we can fix these values, and then we press OK. So the outflow is outflow is going to be the using a sum if, and we add all these values, and we are talking about the outflow from this station, and then we can log it. So this is gonna represent the outflow. So basically we are adding decision variables, which they are exact outflow. They don't have any leakage in the outflow, but inflow they have the leakage. So that's the difference that we have. So we got the outflow and inflow for every nodes by tracking them, and then we can subtract inflow minus outflow, and we can get all the detail. Now, so this becomes net outflow that we have. So let's solve this problem by using solver. So we go to the data tab and solver, and then the objective function that we have is here. The type of the objective function is minimization, and then we select the decision variables that are sitting here, and the set of the constraint that we have is net outflow should be greater or equal to the supply or demand. So this is all the constraint we have, and then we make sure that all the decision variables are non-negative, and then we choose the simple X linear program, and then solve the solution. We solve this constraint. You see that some of the values that we have represented here, they are not integer, but that's fine because the type of the problem that we are dealing is a continuous, the tons of the material that we are sending, and then this is the objective of the material, and then you can see that here we are not meeting the demand that demand of we are not using all the material of the node 4, the cardboard, the type of the material that we have, but we are meeting all the demands of the customer. Also you can see the inflow and outflow of each of these nodes. So basically we solve another type of the problem, a network flow problem, that is more general than the case that we discussed before. Another type of the network problems that we have is a maximal flow problem or max flow problem, that basically simulate the networks of the pipe, like the pipelines of the oils that they are connected, and each of these pipeline are they have a limited capacity to carry oils or water. So in this case we are looking for the maximal flow of the material that we can supply through the networks. this problem that at first they may not be similar to other problems that we already discussed, but you are going to find out that they are very similar to what we have talked so far. So the example of this type of the problem is water that can go through the network of the pipes, or the number of the cars that they travel on the in the network of the streets. So these are the example of the maximal flow problem. But let's look at the clear example of this problem. Let's say we have a oil field and we want to send out the oils to a refinery, which is a station node 6, and we have several pumping stations, station 1 through station 5, and there is a these stations are an oil field, and these stations are connected through the pipes. Each of these pipes, they have a different diameters, so they can carry different barrel of oils at each second. So the purpose in this problem is that we send the oil from oil field to the refinery in such a way that the flow that we have is maximized. So you may wonder, okay, so this is a problem, how can I model it? Because the example that we had is they had a supply and demand, but in this case we don't have a demand or supply. So there is a way that we connect the latest node, the destination node, to the source node by an arc that connects it. So this is we add a new arc. Now we have and then we put for every nodes on this graph a 0. That means the inflow and outflow of each node is 0. And then we define the objective function as maximizing the arc that connects the destination to source. For example, that in this case becomes x61. So this arc, we want to maximize the flow of this arc, and x1j, xij represent the materials that we can ship from node I to node j. So basically we converted this problem to the network problem, and then we can solve it. So the objective function is going to be the x61, and the constraint is for each node we write the inflow minus outflow equal to 0. So in this case for node 1 is x61 minus x62 minus x13 is equal to 0. And and then we have for example station 2. So the inflow of the station 2 is x12 minus x34, and x24 minus x25 is 0. So this is a constraint that satisfies the inflow and outflow of the pumping station. And then we have the capacity, because x12 at maximum can be between at maximum can be 6, but the minimum one is 0, right? We cannot use, we have option that we do not use this pipeline. So x12 has a maximum of 6, and then we have for example for other lines, like for other arcs that we have x24, the maximum of 3. So we have other set of the constraint that we have had. So basically this is a problem, and it's model in the linear programming. Using the similar method that we use for other problem, we can solve this problem. but there is one more set of the constraint that we have. It's the upper bound of each decision variable. We have the maximal flow, which is the last arc that can carry through the all from the destination to the source. So we set up the model, and now let's solve it using the solver. So the objective function is this cell, and the type of the objective function is a maximization, and then this is the decision variables that we have, and the set of the constraint that we have is net flow should be exactly equal to demand or supply, as well as the decision variables should be meet their demand, the upper bound. Hint that here we define a big number as the upper bound of the last arc that connects the destination to the source, because we are trying to maximize this and we need the upper bound for this that decision variable. So we can put a big number which is out of the, it's a lot higher than the boundary that we have for other decision variables. So we can select the decision variables are non-negative, and then we make the simplex linear programming as a solver for this problem, and then we can solve this problem. Now you can see that this is a value that the x1 2 is 5. That means that we are not using the maximum capacity of the first flow line, the pipeline from the station, the oil field to pumping station 1. The maximum, the upper bound is 6, but for our 1 to 3, the station 2, we are using the maximum, and from 2 to 4 also we are using the maximum. So basically the maximal flow of this problem is 9 barrels per second or hours, whatever the unit that we have defines the xij. So if we come back to the problem, this is a representation of the optimal problem that we have, optimal solution of the problem. You can see that we are not using all the capacity of this line, but for the rest we are using the also for this arc we are not using the maximum capacity, as well as this one. So basically we solve this problem using the network modeling. In some of the problems we may have some special constraints, like let's say the summation of the inflow to a station to node 3, it should be, for example, some specific numbers like at least 50, and for station number 4 we should have at least 50. So in this case we didn't have this kind of the constraint in the inflow and outflow, the one that we talked so far. In this case we need to use a little bit creativity, so we can add one more artificial node as a that satisfy the, for example here we are, instead of 3 and 4 we are adding one more artificial nodes that they satisfy the constraints. They are follow the rules of the net flow, and then we add a new arc that connects the artificial node to the original nodes, and it has a lower bound than the one that we already imposed to the problem. So still you can model this one, and we just have added 2 more decision variables and 2 more constraint and 2 more decision variables, because we are adding 1 more arc here. So we are resolving the we still can use network flow of the network, the way that we deal with the problem so far. Now let's talk another situation that we have two arcs with different kind of the cost that they connect to two different nodes together. For example, you have a street with a that one is the regular line and another line is a fast line. The fast line costs more and the regular line costs you smaller, but it has an upper bound. So in this case we can add another artificial node. For example, you can see that $8 and $6 we can add one more artificial node that impose that means that we are separating these two lines and we are connecting just by one line, station 1 and 2, as you can see in the following picture. And the cost of the connecting node 1 to the new artificial node that has been labeled by 10 is 0, but the cost associated with moving from 10 to 2 is exactly the same as the cost that we have here. And obviously the net flow of this node should be 0. And then we can have this line as a as is. So that's the case that we can leave it. The last type of the problem that we are dealing is minimal spanning tree problem. This is a special case of the network that it has n nodes and n minus arcs. So the number of the arcs that we have is less than the number of the nodes that we have, and this is a special case that we should not have any loop in the network. So we are trying to find the set of the arcs that connects all the nodes. We can go from one node to another node, but there is no loop and the connection is in the minimal way. Unfortunately, we cannot use a linear program for this problem, but there's a heuristic way. There is a heuristic way that we can find we can select these arcs. So basically this heuristic algorithm starts by randomly selecting a node and then select the arc that has a minimum cost. For example, if we select arc node 2, you can see node 2 is connected to node 4, 1 and 3, and the minimum cost is 40, so we select this one. And then in the system we have node 2 and node 3, so we consider all of these arcs. For example, arc that 2 4, 2 1, 3 1 and 3 5, and they select the minimum of that. So 2 4 and you can see that 3 6 is the minimum one. So and then we select all the arcs that nodes 2 3 and 6 they have in the system. So let's say we have 6 5, 6 1 and 3 1, 2 1 and 2 4. The minimum one, you can see that across all of this line 50 is the minimum one. So we have nodes 2, 3, 6 and 5 in the system, so we have 2 more nodes, so we have to repeat this process again. And then you can see that we have node 5 4, 5 1, 6 1, 3 1, 2 1 and 2 4. So across all of these nodes the minimum value is a 75. So we add node 4 to the system, so we got all the nodes except node 1, and then the minimum cost across all of the nodes is between 1 and 5. So we got a solution for this problem because we have selected all the nodes and the number of the arcs is 1 unit less than the number of the nodes that we have in this system. So this is basically how we solve the spanning tree. That's a heuristic, and this is a solution that we can get it. So let's start again with another node. Let's say we are selecting node 1. So node 1 is connected to node 2, 3, 4, 5, and 6, and the minimum cost you can see that is 5, right? So 1 to 5 is costing $80, so we can connect this node. So this is first node, and then the nodes that we have across one that connects to other nodes is 85, 100, 85, and 90, and the cost with the cost of the nodes that the cost of the arcs that connects 5 to 4 is 75, and 5 to 6 is 50, and you can see the minimum value is at 50. So then the next node is node 6, so we have selected node 6, and now we have other nodes that other arcs that can be added to the system is the node that connects 6 to 3. So across all of these numbers, 65 is the smallest number, so we can select 6 to 3, so we have the second arc, and then node 3 only adds one arc to the system. It costs $40. So and you can see that this is the smallest cost that we have, so we can add node 2 to the system. So we have node 2, and then across all of these numbers you can see that 75 that connects 4 to 5 is the smallest number, so we select this one. So we have this one. Now we have selected all the nodes, and then we can stop. This is the end of the solution for this problem. You can see that there is no loop, but I have connected all the nodes to each other. So basically this is the last problem of this chapter, and you have seen several examples of the network flow problem. Network flow is one of the most important problems that we may see in the practice. You can use this problem in different ways, so using a little imagination and creativity, you can apply a lot of problems using the network flow problem. So this is the end of the chapter, and thank you.